Every time you load a web page or send an email, data requires a destination. It relies on an IP address, a digital home address that routes internet traffic to your specific device. When the original internet protocol, IPv4, was designed, it had a hard mathematical limit of 4.3 billion possible addresses. In the early days of computing, that number seemed sufficient to cover every machine on Earth. But the arrival of mobile network providers and the boom of the Internet of Things changed the math. Suddenly, we connected billions of phones, watches, and household sensors to the same global network. This map shows how quickly those new devices consumed the remaining supply. Between 2011 and 2020, every regional Internet registry in the world officially reached its IPv4 exhaustion date. Without an upgrade to this addressing infrastructure, the expansion of the Internet would stop. There was simply no room left to add new devices to the existing map. The engineered solution was IPv6. Rather than just expanding the old 32-bit system, this protocol utilizes a 128-bit address space. This shift creates a mathematical limit of 340 undillion possible addresses. That is the number 340 followed by 36 zeros. Managing a network of this magnitude required updated protocols. IPv6 was developed with new tools for address resolution and auto-configuration, specifically to handle these larger datasets. This image shows the immediate challenge for human operators. This is an IPv6 address in its preferred uncompressed format. It requires 32 hexadecimal digits, making it difficult to read or write without errors. To make this 128-bit framework functional for people, engineers established formatting rules to compress the characters visually while maintaining the exact routing data. IPv6 uses a hexadecimal system, which includes the numbers 0 through 9 and the letters A through F. As shown here, those 32 digits are divided into 8 16-bit segments. These segments are known as hextets. The first compression rule allows engineers to shorten the string by omitting any leading zeros within a hextet. The second rule applies to contiguous strings of hextets that are all zeros. These can be entirely replaced by a double colon. There is a strict requirement for this second rule. The double colon can only be used once per address. This ensures that a computer can accurately calculate exactly how many zeros are missing when it reconstructs the address. These two formatting tricks transform an unwieldy block of code into a manageable coordinate that network hardware can easily parse. We cannot simply turn off the old network. For the foreseeable future, IPv4 and IPv6 must operate simultaneously across the same global infrastructure. One migration technique is the dual stack. In this configuration, routers and computers are set up to natively communicate in both IPv4 and IPv6 formats at the same time. Another method is tunneling. This is used when an IPv6 packet must travel across a network segment that only supports IPv4. The IPv6 packet is encapsulated, effectively hidden inside the older IPv4 format until it reaches the other side. These transition techniques serve as bridges, preventing the global internet from splitting into two incompatible networks while hardware is slowly updated. The final technique is translation, or NAT64, used when an IPv6 device must communicate directly with an IPv4 device. The router acts as an active translator, rewriting packet headers as they pass through, so both protocols understand each other. Because these transition tools are effective, many organizations are moving to IPv6-only environments for internal operations. By utilizing these translation protocols and address compression rules, our engineers have successfully updated the Internet's core architecture. These 340 undillion addresses ensure the network can continue to accommodate new devices for the foreseeable future.